Yeah, so anyway, just a brief introduction about me. Happy to dive into Articraft now. So yes, so Articraft is a agentic system intended to generate articulated 3D assets at scale, particularly for like downstream, a lot of downstream kind of use cases, such as training other neural models, or for other things such as like VR or simulation. Yeah, so the problem is that, articulated 3D assets, objects with moving parts and physical joints, are necessary in a lot of like downstream applications, as well as for training data. Authoring each asset by hand in 3D tools is slow and demands a lot of skill. Existing articulated data sets are very small and narrow. And learning-based methods often overfit the scarce data and fail to generalize, as we noticed in particulate. Data really is a central bottleneck for understanding articulated 3D. So maybe some of you guys are familiar with this. It's called the PartNet mobility dataset. This is actually a dataset that is still commonly used today. It's quite a small dataset of articulated objects. These are all like this is an example of something that you would see in this articulated in this data set. As you can see, like, a lot of this stuff is like hand done by humans. It's not always accurate. There's a lot of inconsistencies. There aren't a ton of categories either. And you can see for each of the categories, such as box, there's only like, 28 or so samples. So yeah, small data set, quite narrow, lots of like little mistakes here and there. So our idea was to essentially generate articulated assets as code. We noticed that, for example, like if you were to ask an LLM about, give it an image of, let's say, an office chair, the LLM actually intuitively knows and it has some sort of understanding about the kinematics of that object. So if you give, I don't know, GPT-5 like an image of a chair, um, it'll tell you, okay, like this chair is supposed to, can lean back, can go up and down, etc. The issue is that how do we translate this into a form that would actually be useful, rather than just having the LLM describe things in text. So our idea was to really have the agent write code against a custom library that we had written, that essentially allows the LLM to create these like articulated 3D objects. So there's the LLM-friendly SDK, which allows the agent to specify parts, geometry, and joints, plus tests, so the agent can validate its own assets. There's a minimal harness, so the agent can really focus on this task. It edits a single program, runs it, gets feedback. And we also try to use off-the-shelf LLMs. So, GPT-5, Claude, Gemini, etc. We also want to stay really light, so like no blender, no image feedback, so generation stays like cheap and scalable. Um, so yeah, that was a big goal as well because we want to generate a lot of data. So we're really trying to balance between, making the best possible 3D assets as well as making like affordable 3D assets so we can scale it up to, an arbitrary amount of data points. Yeah, so we built Articraft 10K, which is over 10,000 curated articulated objects across 245 categories, which is a huge amount of categories in the space. We did some user studies. Overwhelmingly, users preferred the Articraft assets. We show that it can boost downstream models. There's some assets that we consider simulation ready. And most importantly, we released the whole project openly, including the data set, the code representations for those objects, agent traces. So we also released like the agent reasoning and also like the tool calls that the agent took to actually generate these objects, especially for future like post-training on the environment, etc. So all this is available on GitHub. This is an example. So we also built a really beautiful viewer for the data. So you can see here that this is a snippet from our viewer. You can see that this is an object generated by Articraft. You can see the prompt. You can rate it. This is all open source, and we're trying to source like data from the community. This is from one of the data points. So you can see here, I'm scrolling through the code as well. So you can see the code that generates this particular object as well. Yeah, so this is kind of a rough sketch of the pipeline from the paper. So there's an agent workspace here. Essentially the workspace in which the agent actually does its work. Essentially like reads over documentation, commits code files, etc. There's an action space that the agent can take, which is like reading the file, editing the code, finding similar examples, compiling the model and getting feedback on the model quality. And also finally something we call probe model, which is like essentially like queries that the agent can execute against the model. So it can be like, okay, like for these two parts, I need the distance between these two parts. Or for these two parts, do they overlap? And if they overlap, like can you calculate like how much it overlaps by? And the agent essentially uses this to reason about all of these objects geometrically in code and also just purely in text. So you can see here, for example, this is an example, like this is kind of a stylized representation of what happens. As a prompt, the model does some research, the agent does some research, implements a first version, there's some errors, there's like feedback from our environment and our SDK about the errors. It goes in this loop, fixes things until finally it receives like a successful compile result. Yeah, so this is the model.py. This is the file that the agent modifies. Yeah, so this is also an example. So when I say the harness, I'm talking about like, the agent runtime. It's helpful to look at some examples that the agent what is the agent actually receiving in terms of signals. So this is an example structure of what compile model returns. As you can see, there's every signal is tagged with severity, whether things are strictly a failure, warning, etc. There's the source, like where is the signal coming from. Codes are very specific and very informative for the agent. So, like, for example, there's compile runtime failures. There's like quality control overlap, quality control isolated parts, etc. So all this is kind of like structured and coded. So the agent knows exactly how to address each of these problems and whether to escalate, ignore, etc. So this is kind of like the geometric reasoning of feedback in text. Oh, feedback also escalates on repeats. So basically, if the agent keeps on failing, the system also starts modifying the feedback and starts escalating the severity of certain things. Yeah, so the agent stops when it decides that it's done, so it submits no more tool calls. And then we also let it finish if the code is valid. There's a couple other exit conditions. There's also like max turns. We set like a max turn cap. There's a cost limit because this, after all, like this is a system that we intended and we used to generate like huge amounts of data. So we need some kind of like cap on some reasonable limits. The last thing is also like an error. So if there's a runtime exception, if there's like other errors that the LM cannot continue, we also exit early. But otherwise, in normal circumstances, 99% of the time, the only exit is when there's a clean compile on the current revision, and the agent calls no more tools, which is similar to the design of like other useful agents like Codex or Cloud Code. Yeah, so the SDK that we built provides quite a bit of things as well. The agent writes a program against this SDK, the Articraft SDK. There's an object model, which includes the articulated object, parts, articulations. There's like geometry primitives. There's procedural meshes that we take inspiration from CAD programs, such as extrude, lathe, loft. We also expose like low-level access to CAD query, even though most of the time the agent is writing against our like Articraft, like pure Articraft SDK. There's a lot of benefits to like a pure Articraft SDK here. The fact that we calculate collisions precisely is a lot simpler for the agent. So most of the time it's writing against primitives and procedural meshes. Um, we also include semantic parts for common parts of the object, such as like wheels and tires, joints. There's also exports. Yeah, quite a full-fledged SDK. Testing is built directly into the SDK. So this is really important. A big part of how the agent is able to create such complex objects is because of the full feature testing that's built into the Articraft SDK. So there's a baseline quality control. So we always, for example, assert like sanity checks, such as like there's only one root part, the model's valid, every mesh asset resolves, et cetera, et cetera. The agent itself can also write custom tests. So it can like expect gaps, expect contacts between objects to use that to test whether things are, inserted correctly into each other or, maybe they're not overlapping. The agent can use context and judgment to write those object-specific tests as well. And also, our baseline quality control is like a static signal. And obviously it can be noisy and it doesn't always apply to every like object. So the agent also has the ability to allow overlaps or allow isolated parts when it's semantically correct. That's really important because otherwise, if it's just the static quality control, sometimes the agent can get stuck. The quality of the signal is not very good. So the agent can modify the signal as well contextually. Yeah, this is an example of a test, a real test that the agent wrote. As you can see here, it calls with context pose. So it poses the object to a certain essentially articulation. And it expects like overlaps, expects gaps. It wrote all these different tests. So for example, this expect overlap, it's expecting that the draw tube and the telescope actually overlap with each other. Essentially that the draw tube goes inside of the telescope. So this is an example of a test that the agent can write. Yeah, so this is an example of a trajectory, the same telescope trajectory. As you can see here, compile model reported like a compile runtime error. It didn't write the code exactly correctly, so it fixes that. There's an isolated part that it reports, so like the draw tube and eyepiece tube float, 7 millimeters off the body. So the agent responds by widening the offset bridge so the flowing group reconnects, et cetera, et cetera. So you can see here how the signals play into the agent response. Yeah. So there's a lot of different examples of this. This is like, yeah, this is an example of like what the harness returns when there's like multiple compile failures in a row. And this is some snippets from like an agent reasoning on one of the traces. So I can see here, like, this is a debugging reasoning. I'm looking at this design, immediately recognizing a potential issue, et cetera, et cetera. I could keep the overlap and add an allow overlap flag or modify the barrel definition. So you can see the agent's actually reasoning about the signals quite accurately. And also the top reasoning is from a planning stage from the prompt. Yeah, these are some example of generated assets from Articraft. As you can see, like some of them can get quite complex if you look at the wheelchair, if you look at all the articulations on a keyboard. This is the telescope we talked about, satellite dish, tower crane on wheels, boxing on with control knobs. So yeah, there's quite a wonderful, like, because we're building this on top of like, frontier LLMs, you get all the benefits and all the generality of the frontier LLMs. You can generate really quite a wide array of different types of objects. Yeah, these are some comparisons of text prompts and other, text to 3D kind of models. You can see here that, this is vanilla codecs as well. If you just give this prompt to codecs and ask it to make the object, as you can see, we make quite complex, much more complex and full-featured things using Articraft. Yeah, this is some user study rankings. As you can see, like most people prefer Articraft. And this is a really interesting diagram here. This is kind of the downstream model results. So as I mentioned, I was initially going to help out with a project called Particulate, which was a neural model. And as you can see, this Particulate before adding Articraft data really struggled on outer distribution data such as range hood, stand mixer, stovetop, and even a small sampling, like 40 or 50 different like synthetic examples of range hoods generated using Articraft leads to huge improvements on downstream metrics when mixing in this synthetic data. Yeah, so these are some base model ablations. As you can see, this is how like reasoning kind of affects the shape of the object. As you can see, like as we go from low to medium to high, the object gets more and more complex. Yeah, so this is kind of an example of all the different objects that are created. This is a video that we pushed on Twitter like a couple weeks ago. Yeah, so there's a huge variety of objects. As you can see, there's like buildings, there's swings, there's fans, etc. That's part of what makes the Articraft data set quite special. Yeah, and you can see it can get like very complex. So it can generate like, turbines, different like mechanical structures as well. You can see back here, there's like a scooter, there's a bench, yeah, gates, yeah, different mechanical things. Like this is the axle of a car. Yeah, so again, we're piggybacking off a lot of the wonderful generality of the LLMs. Yeah, there's a lot of articulated assets. As you can see, there's 10.7 K-map records. Not all of them are suitable for downstream training. But yeah, all these are hand rated, so you can see like there's an average stars, average cost. The data set is like extremely rich. There's a lot of like things that we're tracking, like the average input tokens, average output tokens. Yeah, tracking a lot of things about how the agents perform, which categories are more expensive. Yeah, tons of data here. Yeah, this is an example of like another object from the viewer on the website. There's also a lot of like, we can, for free, we can get image conditioning just from the behavior of like frontier models. This wasn't really the focus of our paper, but it's something that we studied a bit just to see like, how well the agent can handle like image conditioning, which is quite good, just out of the box. Yeah, this is another example. So how Articraft can be used as part of other pipelines as well. As you can see here, we're going from a video of a room using light reality and Articraft to go directly to like a 3D, like articulated version of the scene. Yeah, some of the assets are also able to be put in simulators and used with along with like robotic policies. As you can see here, this is an Articraft generated oven, and this is an Articraft generated desk as well that's articulated. Articraft can also be used in like other downstream applications such as VR. As you can see here, like we're manipulating a lot of all these are like Articraft data set, Articraft assets, including the fridge. And this as well, the robotic arm itself is also generated in Articraft. Yeah. So that's Articraft. Yeah, thanks for listening. And yeah, happy to answer any questions.
Yeah, thank you, Matt. That's so amazing. I mean, I love to see all these demos and on Articraft, and then yeah, it's so amazing. Yeah, feel free to drop any questions that you might have in the chat, or if you like, you can maybe open the mic if the question might be a bit long, just to chat with Matt. I mean, it's a valuable uh opportunities. Um, okay, yeah, so basically there's a question in chat. I'll just read it out. And yeah. So question from Navi. Did you use other models such as Gemini for comparisons?
Yeah, we actually did use a bit of Gemini. Most of the data set is generated on 5.5, and that's just purely because of like cost reasons. So we just had a lot of like credits on OpenAI. So we use mainly OpenAI, but Gemini is a phenomenal model, particularly at these kind of 3D and like multimodal spatial reasoning tasks. But we just had like practical concerns. Because yeah, it wasn't like I mentioned for Articraft, the goal is not to create the most realistic 3D models. The goal is really like a scalable, lightweight platform to generate synthetic data. And we're really intending on using it and scaling up the data set to use in like downstream training. So we we had to like essentially like maximize the resources we had to generate Articraft 10K. Yeah, I would say Gemini is better, but Gemini is also like much more expensive, I think. It works for longer, consumes more tokens, etc.
Yeah, thank you, Matt, for answering. Any more questions? Anybody? Yeah, go ahead.
Hi, thank you, Matt, for the amazing talk. I got a question about how does this compare? I guess you mentioned in your experience as well, like maybe Neo's 3D mesh generation model. how does the like generation space compare to the neural approach? Like, uh, does it limited by the SDK that you created, or like what's the limitation about the generation space and also the quality compared to neural approach?
Yeah, there's definitely limits. I think like yeah, there's a lot of pros and cons. Obviously, I think neural methods can handle a way more vast array of categories. As in like neural methods, for example, like if you wanted Articraft to generate like a realistic splat of like a realistic model of like someone's face with like hair, that's like not possible. Even in like very complex like computer programs, like it's very hard to do that. Um, but neural methods can handle that quite well. One major thing though is that because we're studying like kinematic structures, a big goal of Articraft is to generate like not just 3D objects, but 3D objects with like correct kinematics. Um, I think some of the issues is that like neural methods tend to bias towards visual fidelity and visual detail. And a lot of the data generated by those neural methods are not necessarily useful for downstream training tasks because, or even downstream applications because the meshes are like they're not clean. They're very like, there's little mistakes here and there. There's like missing triangles, for example. Or if you generate like a 3D articulation, maybe the articulation axis is not like completely clean, right? So this kind of stuff the LLM solves for quite well. The LLM when defining the articulation axis is very easy to define in code that, I want like a 90-degree like angle on something, right? But like that's maybe more hard to do like extremely precisely in neural methods. So there's a lot of trade-offs here and there. I don't think Articraft again will displace neural methods. But it's more of a study of how we can like almost distill some of this knowledge from LLMs and use it to generate like useful synthetic data in like data poor regions, which is, articulated 3D objects is not very it isn't like a very data rich space. Finally, I think like I will say this is not the goal of Articraft, but I really think that like LLMs right now, in terms of like 3D understanding, 3D generation, CAD, is just starting to show like what could be possible in those spaces. So I think it's like a full generation behind. For example, like where we are with text, 3D generation in CAD using LLMs is like a full generation behind, like GPT-4 era essentially. But it's totally feasible to think about someday when LLMs can be good at enough at CAD and 3D design to actually completely displace neural methods when it comes to like manufacturing, industrial design, etc. Where actually I think computer programs can capture like a huge percentage of those objects.
That makes sense. Maybe one more follow-up question to that. So, you mentioned maybe one of the limitation is I mean, there are not that many like articulate objects data, 3D objects data. Uh, uh, so from the like, I mean, this is I mean, your approach is one way to scale up the data set. From the like scaling law perspective, what do you think will be the future? Like, it seems there are like two way to like scale up like the generation. Either like maybe you just have more train on more like code generation for 3D, then the model can generate better 3D object by code, articulate object by code. Another approach could be like you just take all those like generated objects maybe and maybe collect more object data and maybe add one in the future maybe add one like more modality to the multimodality model, right? Maybe now they can generate image token, video token. Maybe in the future they can generate like 3D object tokens as well. Um, what do you think will be the future, like more towards the coding approach or the maybe more like native modality approach? Yeah.
Yeah, I think it depends on your use case. I think if you're doing just like visual fidelity, like I don't know, your Apple making like the VR headset, right? It doesn't make sense. And like you're doing like pure VR entertainment, it doesn't necessarily make sense to make everything in code. Because it's like limiting, it's slow, etc. Whatever. You want to like output the 3D object directly, right? But if you're working in something like manufacturing or industrial, or like CAD, it's useful to have a useful representation downstream. And like code files are extremely useful. So if, for example, if your code file can like tie in with like Revit or Autodesk, right? If you give me like a mesh of like a car axle that's like functionally useless to me in Autodesk, right? If I actually want to design like a new like car axle, let's say I want to design like a new like car battery system or something, I need the actual code files. Like I need a useful format, um, rather than the LLM just chunking out like a 3D approximation. And as we said, like the, like 3D, for visual fidelity, it doesn't really matter. But if you're doing actual downstream tasks, like if you want to like load it into simulation or if you want to like load it into like Autodesk or something, you really need like clean meshes, like clean lines, like clean data. And code is a way to really ensure that.
Awesome. Yeah, that's my question. Thank you.
So, thanks.
Yeah, thank you, Goha, and it's Matt for answering the questions. Okay, so three more questions, essentially two more. So yeah, for the question from Yunfei, for the benchmark, we observed that rare objects are harder to generate, right? So how do we evaluate the quality of a generated object?
You said rare objects?
Like a rare object.
I see,
Oh,
yeah.
so
So
yeah, in the chat area, you can also read it.
gotcha. Let me see. Okay, sweet for the eventual. Yeah. So rare objects are hard to generate. Yeah. So the quality of a generated object. So what we did for Articraft 10K is we actually like hand we hand rated every object um for the first 10K. So we understand like the rough spread of like, 5-star, 4-star, 3-star, 2-star, 1-star objects. So to answer your question for this project, we hand rated everything. And we only flowed in 4 to 5-star objects into into the downstream model training. The vast majority of these things, like, 80-90% are like 4 to 5 star. Um, that being said, I do think, like we're trying to like community, we're kind of try and drive like community contributions to this data set. Those should be hand rated. And I think also like in the future, this isn't something that we explored in Articraft, but definitely creating like, LLM judges, et cetera, to like judge the visual quality, judge the code quality, for example, can also be like a useful like filter for some of these objects as well. But yeah, it's not something that we like explored automating in Articraft and in this version of the paper. But for us, we actually like I hand rated a lot of the assets as well as like the rest of the collaborators as well. Yeah, thanks for the questions. It's a really good question. Okay. Do you
Amazing.
still consider adjusting it after it is generated? Why choose Python's intermediate language control? Seems like Blender. Oh, yeah. So I think it's a good question. So first of all, no, we don't consider adjusting it, even though we can. There's no reason to not. But we're really trying to generate like a full-fledged like we're trying to have as little human in the loop as possible because we want to generate as much of this data as possible. So the agent harness is also designed for one-shot generation, which is different. So going from prompt and image plus optionally an image straight to the final like form. This is because we don't want to like, hand tune. We're not trying to create like productivity tools. We're trying to create like synthetic data pipeline. Python just because it's easy. I think it's easy it's like token efficient. Like what you can express in Python is, small lines of Python, you need more lines in other languages. LLMs are good at Python. Yeah, I don't think the medium was like something we considered very carefully, but yeah, Python is just like token efficient. So yeah, and yeah, thanks for the comment about the e-commerce for industrial products. Yeah, I think yeah, again I think yeah, like code for generating CAD is for sure going to be like really useful. But it's like a full generation behind. I think it's something that like people are starting to think about, particularly at like large model labs. And honestly, like code scaling lends quite nicely to like generating better CAD is something that we realized, hence the code medium. Yeah, so I'm very excited in the coming years, like honestly, like the next like 1 year, as you know, like coding gets more saturated, like and LLMs spread to like new domains such as like CAD and 3D modeling. I do think it's going to get a lot better. And this is kind of like an early preview into like what's going to be possible in the future. And
Yeah,
then, okay, Ahmed
yeah.
said, what do you pass to the agent as context when editing the object? Is there an object mesh representation code? Yeah, so we only pass, the agent only gets this one thing called model.py. Um, yeah, so this is like an example of, yeah, it only operates out of a single file, which is model.py. Um, yeah, and the model.py encapsulates everything. Yeah, let me see if I can show you exactly what I mean. So if you go here, sorry, it's lagging. Cool. Okay, yeah. So if you see here, somewhere in the video, yeah, so you can see here I'm scrolling on the right. This is the code that generates this like very complex robotic arm, as you can see, using our SDK. So that's the context that it gets. Okay. And then Sheber says, is it possible to extend the SDK to support soft body deformation simulators such as those for organs? No, yeah, definitely. I think you definitely can. I think that's kind of the beauty of code scaling is that like, you don't like LMs are already like very good at code. They're only gonna get better at code, and their spatial reasoning abilities are also only gonna get better. So we obviously have like a deadline for this project. We need to like submit this paper for NeurIPS, but if we had like a full team and like we continue to like work on this, we definitely extend the SDK further and further. And also most importantly, the way I designed the agent is via something called like progressive basically, like we progressively reveal more and more of the SDK as requested by the agent. So the SDK can like scale to an arbitrary size, and the agent can actually like search for the relevant docs that it needs, the relevant pieces of code that it needs to make that specific object. So yeah, we can scale the SDK like a bunch of different ways. And I don't know, for example, like I added like gear support to the SDK, and then all the new generations, the agent can know how to like add very detailed gear mechanisms, for example. So that scaling axes of just like making the SDK better. Um, yeah, there's still tons of room there. And by the way, this is like an open source project. So all the data, everything, the harness is all open source. Like if any of you guys want to make contributions, yeah, please like pull PR, pull issues. Yeah, I'm more than happy to accept contributions. Yeah. Yep. Exactly. Yeah. I think like radiance field-based methods are like really focused on visual realism. So like for example, like if you're like I said, if you're Apple and you're making like a VR headset, then yeah, of course you're gonna think about like neural methods because you don't actually need a useful representation downstream. You're kind of just like talking to this like floating head, right? But if you actually want to have like useful representations, and unless if you believe that, we're gonna all be in like we're no longer gonna have like useful tools in the future and everything's gonna be generated via some big neural model that spits out pixels, you know? Um, yeah, I think we're still gonna need like useful representations down, like interoperable representations. And code is really like one of those interoperable representations.
Yeah, amazing. Thank you, Matt. Okay, there's a question from Wei Jie.
Is the model mesh based? Yeah, it's mesh based. Um, Well, we built this for like initially for a single model downstream, which is called Particulate. So yeah, it spits out like a URDF, which is like a standard like art kinematic like format for like especially in robotics. Um, yeah, and there's tons of edge cases. So like one major edge case is like for example, if the object gets like really complex, the agent struggles to like resolve like for example, if the agent blows up on the first try for a really complex object and there's like a million compile signals, the agent's really going to struggle to like chunk through all those issues coherently because you know 3D is kind of complicated where like for example like if you have a complicated 3D object you move one thing it can like trigger like a million other problems, right? Maybe you solve this one floating part, now you're overlapping with like three, four other things. Um, so it's very complicated. Like there's some sort of like geometric reasoning that needs to happen. I think another thing is that it'd be, we didn't really explore like image conditioning or um, image feedback. I think current models are not very good at general image feedback. So if you give it like an image of like, this part that's like overlapping, it has a really hard time telling like the quality of it just from the image token. So there's a lot of improvements there. Um, Obviously for huge classes of objects like organic shapes, it's really bad at. So if you ask it to make like my face or something, it's gonna really struggle. Soft body objects, etc. Um, yeah, but like I said, I think sometimes we chase like I think like these um kind of things will get a lot better. I think the current generation of models is like a full generation behind. So like Articraft is kind of like the GPT-4 equivalent capabilities. It's like kind of cool. It's like kind of you can see a glimpse of what's going to happen in the future. It's not really that useful for useful work yet. Um, yes, but I think like definitely there's a strong path to actually scaling the geometric reasoning and also coding capabilities to get there to get to one day be like I need this kind of object, I need it to be like 3D printable, I need it to be like etc. cost with these materials, and the agent can resolve all those to design the object for you and get like 80-90% of the way. Yeah, hopefully that's helpful.
Yeah, that's really, really helpful. Yeah, thank you, everybody. Um, and then maybe so I will send it again. So I think this one will be the paper link as well as the GitHub link, right?
Yes, yes. And also like a big goal of Articraft is to make it easy for people to like share data. We're really accepting contributions for like, for example, this arm right here that's on the screen is actually like contributed by someone that's not on the project. They just opened up a PR and push this to the repo. So yeah, we're accepting like contributions for data. If you want to like modify the SDK in any way, open up a PR. Yeah, it's an open source project. And we'll be extending it, improving it, and yeah, I think we'll see more versions of Articraft in the future.
Definitely. So what would be the end goal of Articraft? So
I think it's kind of funny. I think like 3D is such a big space, and I think like people are like interested in like a huge diverse range of things. Like some people like on the team really want to use this for like, games, like, putting these kind of things in a game, which is are honestly like a pretty good application, I think. Because the quality and precision bar is way lower for games than for let's say simulation. Some people really want to explore like scaling this for CAD. That's a great option, I think. And some folks want to use this for like in sim robotic training. The beauty of this is that the method holds for most of these. What really changes is like, the SDK needs to be adapted for games, or the SDK needs to be adapted for like CAD or like simulation robotic training. And then you also need to adapt the harness signals. So for example, in simulation, we might care less about details, but we really care about like having really clean articulation, for example. Versus in games, we might not care about like super clean articulation, but we really care about having like, a visual style or fidelity. And the beautiful part is that you don't need to like retrain the model or anything, but you just need to like adjust the SDK and adjust the signals that you're returning back to the agent to shape this. Yeah. So like the harness itself, like talked about, we kind of have like returns like signals, like codes, etc. These are kind of like reward signals for the agent. In fact, like in early on when we are working on this, a big part was like really nailing these return codes because sometimes the agent will try to like reward hack and like do like crazy things in the 3D object to just try to bypass these codes. So these are like the reward signals that our system is returning back to the agent to shape what its outputs look like. In this specific case in Articraft, they're shaped between a balance of quality, visual quality, and also like kinematic fidelity. So it's right in the middle. So it's perfect for synthetic data. you might want to go more towards kinematic fidelity if you're doing simulation. You might want to go more towards visual if you're doing like gaming assets.
Yeah, that's amazing. I mean, that's great. Yeah. And so basically in Camel we will host in Camel and Nigen, we will host the live talk every Friday and maybe like one in another Friday. And then yeah, we'll invite like guests like Matt and then people who are interested to share their project or paper. And then, yeah, I mean, Matt, thank you so much for your sharing, and thank you everybody for your active engage. And yeah, as Matt mentioned, it's open source, and then we're calling contributors here as well. Yeah, and then if there are no more questions, I mean, is there more, Matt, you want to talk to everybody or good?
Yeah, I think
Yeah.
just thank you guys for having me on. And yeah, thank you guys for all the excitement and questions. I really appreciate everyone's time.
Amazing, thank you. And this one is recorded, and then I will share the recording file to our Discord and the group chat. So yeah, thank you everybody again. And then we can maybe call it here. Thank you, Matt.
Perfect. Yeah.
All right, thank you.